Welcome back, guys. I don't know how to weight the importance of this video, but if you're interested in nuclear issues or nuclear science, maybe that's why you're watching. Again, good background, good physics, but usually chemists don't talk about nuclei. They talk about electrons and valence electrons and the energies associated with the breaking of chemical bonds. But oftentimes there are changes, nuclear changes, with especially large nuclei that, of course, are associated with a lot of big energy change. Not all nuclear stuff is nasty and dangerous. We've manipulated so many of the elements to create isotopes that are radioactive that are all very useful in medicine, diagnostics, even in food processing and such. Here's a little demonstration I'll probably show you in class if I have time. Make a little cloud chamber. You take a piece of dry ice here and put a cloud chamber on top of it where we have an alcohol vapor chamber with a lantern mantle, which is an old-fashioned way they used to make, I guess they still do make them, burns white gas when you're camping, and this mantle, when hooked up, glows white hot, gives off a bunch of light. But in this, it just so happens that this lantern mantle, as they call it, this little piece of cloth, has radioactive thorium-232 on it. It decays to give off alpha particles. Anyways, as you can see, this is not the topic of this video, but there are equations called nuclear equations, nuclear decay, nuclear transmutation equations that balance the number of protons. Down below, 88 and 2 make 90, and 228 and 4 make 232. Of course, changing from 88 to 90 changes, in essence, the chemical element, radium to thorium, or thorium to radium. And this is called an alpha particle or a helium nucleus, also abbreviated with the symbol alpha from the Greek alphabet. I really hope I have time to show you that demonstration. It's pretty cool how you can see the results of the radioactive decay of the thorium. Way back in the olden days, about 110 years ago or so, 115 years ago, they were trying to understand the nature of radioactivity. They knew that these rays, back in the day they called them X-rays, but they didn't know that X-rays and gamma rays were part of a slightly broader class of radioactive, what we call radioactive decay products. Phosphorescence, I might have talked about it earlier, not in a video, but in class. It's not per se related to radioactivity, although materials that glow in the dark, phosphorescence, they are excited or excitable by the X-rays and the gamma rays and the radioactive particles. So Becquerel was trying to figure this out, and he indeed decided that almost all of them at the time that they knew of, these radioactive rays came from uranium products, uranium ores, uranium materials. It seemed like energy was being given off from a rock, and they didn't know where the energy was coming from. This uranium-containing rock exposed photographic film and had other weird properties of giving off the radioactivity. Indeed, Marie and Henri Becquerel, super famous scientists, I think Marie Curie was the first to win 2 Nobel Prizes. Of course, the first woman to win a Nobel Prize for her studies in radioactivity and other things. Sometimes even, to be confused with the previous slide, glow-in-the-dark paint from old-fashioned wristwatches can actually have a low level of radioactivity in it, but that's not per se why it glows in the dark. It's a long story. Glowing in the dark, giving off energy with limited input. 2 elements named after her for her discovery of them. A simple device we can use to detect radioactivity is a couple of metal foils hanging down inside of a glass jar, make them positively charged. Then you hold something radioactive up here that doesn't visibly interact with these 2 prongs, and you don't touch them, but the radioactivity can zap away or take away or somehow carry away the positive charge or even give negative charges to the foils to neutralize them, and the foils go down. Called an electroscope. Way retro, old school. These days we use a Geiger counter. Other properties of radioactivity: they ionize things, they change them into ions, they have a lot of energy, they can go through pieces of paper, shirts, 2x4s, even concrete, depending on how high of an energy ray. I don't like that word ray. It's not very descriptive. Or what, depending on the level of energy of those particles. Excuse me. It turns out the most ionizing particle is the most highly charged particle. That's the alpha particle. It has two positive protons and two neutrons. This is the helium nucleus. But the most penetrating ray is usually with the most energy are the gamma rays. And way back in early chapter 2 of Gen Chem 1 we studied E equals h nu, and the frequency of these are so high and the energy of these gamma rays and x-rays are so high they can penetrate through tissue and make, say, an x-ray. The bones absorb the x-rays. Gamma rays probably travel right on through the bones too. So these are super high energy, can cause DNA damage. These are stopped even by your skin, so that's not such a big deal with the helium particles, but they do ionize things pretty well. I've heard of electrons, but what about positrons? Have you heard of those? Whoa, it's kind of crazy. These numbers try to reflect whether it's a nucleon or not and how many nucleons are all together there. I'll talk about that probably in my other video when we talk about nuclear equations and balancing those. Will I? I hope I do. I should. Alpha particles, beta particles, gamma rays, gamma waves. These are electromagnetic in nature. They have no mass, but they're also very penetrating and very damaging to DNA because they're so high energy they can damage the mitochondria and the DNA, and if that DNA is continually bombarded and can't repair itself and the mistakes replicate, it causes, of course, eventually cancer. Positrons are less common because they're like antimatter, if you know what I'm saying. Maybe you want to take a course in modern nuclear physics. Chemistry department doesn't really offer one like that. Maybe the radiology department. Nuclear notations, we studied this again way back in chapter 3 or whatever. The symbol goes here, carbon, and the atomic number of protons, and the total number of nucleons in the nucleus up here. So this is carbon 14 isotope, carbon 13 isotope, carbon 12 isotope is very, very common. Carbon 14 isotope is very, very rare, and we can use the radioactive forms of carbon 13 and 14 for finding the age of old once living things or tracing the flow of one compound in a system. When I say important, I'm not sure how important they are actually. I know what the proton is, I know what the neutron is, I know what the electron is. The alpha particle, that's good to know as well. Alpha and beta. The beta particle is the same as an electron. Positron, very unusual. Don't lose any sleep over that. And honestly, like I said in the very beginning, I don't know how much of this will be on the final. Probably a very limited amount. Naturally occurring in the dirt of southern Utah, uranium ores, they naturally decay alpha, beta, beta, alpha, 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 beta, beta, alpha, beta, beta, alpha to get down to lead. And that series of decays takes a long time. On any one particular uranium-238 atom, it's a statistical probabilistic likelihood of taking X number of years to go from here to here. Each of these decays has their own half-life, usually pretty long, like years and years, sometimes very fast. In any case, we could make a summary of that and say uranium decays by 6 alphas and 2 betas. And I could say, well, what would be, if I knew the 6 alphas and 2 betas, what would be the ending product if I didn't already know it was lead-206? I would say, well, let's see, 6 times 2 is 12, 2 times negative 1 is negative 2, 12 plus negative 2 is 10, 10 plus what number gives you 92. 6 times 4 is 24, 2 times 0 is 0, 24 plus what number gives you 238. And if you write those numbers down and look up element 82 on the periodic table, of course it's lead. We'll talk more about those nuclear decay equations. But if you want to practice one, here's one to practice, and I'm gonna scroll on by it just because I think it's all sort of self-explanatory. Did it say how many alpha and how many beta? So if I was going to take berkelium, I think that is, and go to lead, I would say my alpha particles change the proton number by 2. So how many? Oh Lord, that's going to be a tricky one. They also change the total number of nucleons by 4. So 247 minus what number gives you 207? Isn't it 40? So wouldn't this be 10? 10 times 4 is 40. Once you have that in place, you can do a little more math. 82 plus 20 is 102. 102 plus what negative number gives you 97? I think it's 5. Whoa. Exercise in logic. Which of these are alpha decays? Alpha has a 4 nucleons altogether, but so to have a 4 up here and a 2 down in the proton number. So I think it's what is it? This is this one. 85 plus 2 is 87. 208 plus 4 particles altogether is 212. So I think this was the alpha decay. And we're almost done. Carbon 11 decays, transmutes, changes the nucleus, changes of the unstable carbon 11 nucleus into boron 11. Still have 11 particles total, but the carbon has 6 protons and the boron has 5 protons. Peek over at the periodic table. Yep, true. So something happened to the number of protons in this carbon 11. The proton must have changed into a neutron so as to keep the total number of nucleons the same, but the proton number went down from 6 to 5. 5 plus what gives you 6, and 11 plus what gives you 11? Well, it's 0. This is called a positron, the antiparticle, the weird anti-twin of the electron. Now, that's not enough info on the nuclear equations for most of us, so I think I'll have another video with regards to that. But thanks for watching, and I'll shut the heck up. Thanks for watching, guys.